much for choosing this talk over the sunny weather outside. So today I'll be introducing you how to deploy your own data science environment in the cloud using open source projects such as Jupyter and Kubernetes. So yeah, I'm a software engineer and a data engineer, and I've mostly worked with Python, Java, and Go, and in data-heavy industries such as finance and machine learning. So I also run a platform called Spime Labs, which helps people deploy managed JupyterHub solutions in the cloud. And yeah, I love talking about Python or coffee and cats. So if any of those are interesting, come find me after the talk. Right, so by a show of hands, who in this room already uses Jupyter Notebooks for something? Okay, almost everyone. So you'll be very familiar with this user interface. This is a demo that I've set up at pydatademo.spimelabs.io. You can log in with GitHub and have a play around if you so wish. Let's hope it doesn't crash. But basically, yeah, a Jupyter Notebook is an interactive computing environment that allows you to run code, produce graphics, upload files, and things like that. So it's very useful if you're running a big team or teaching a data science class or have a research group where people need to be able to run code in various kinds of languages. So the Jupyter project began its life as an interactive Python computing environment called IPython. It was first developed by Fernando Perez, a PhD student at UC Berkeley, I believe. And those of us who've been around in the Python community for a while remember this as the better version of the Python shell. So since that point, the IPython project, which is now known as the Jupyter project, has grown to support a large ecosystem of programming languages. So these days, it's not just for Python programmers and data scientists, but also our friends in the R community and the Julia community. Among, I think, 100 other programming languages can take advantage of this computing environment. In addition to supporting lots of different programming languages, there are also many auxiliary sub-projects, such as JupyterHub, which helps you manage a large-scale deployment of Jupyter, and also Jupyter Lab, which is the next-generation user interface for interactive computing. So in addition to this, there's a very active open source community around this project. There is a conference that takes place every year in New York about Jupyter. And in addition to that, it's been adopted across a wide variety of scientific disciplines and industries. And very recently, because of the improvements in the user interface and the large ecosystem of data science packages that it supports, it's been seen as a serious contender for proprietary solutions such as Mathematica. And if you're interested in things such as reproducible research and being able to share your code, you should read Paul Romer's article where he compares the Jupyter project to Mathematica, and he explains why it's been better for reproducible science that people are moving away from closed source proprietary solutions. So in addition to JupyterHub, which I'll be talking about today, I wanted to bring to your attention two new projects that are gaining some ground in the Jupyter ecosystem. So the first one is Jupyter Lab. It was released a few months ago, and it's the next generation user interface. So as you can see from the screenshot, it's a bit more advanced in the sense that it allows you to do more than the classic Jupyter notebook user interface that I demoed a while ago. And the second really cool project that's been recently deployed is BinderHub. And this allows you to create custom computing environments from a GitHub repository. So if you're interested at mybinder.org, you can put in the URL of your GitHub repository, and it will spin up a Jupyter notebook with those dependencies installed. So it's actually really cool. If you want to share your work with someone else, you can simply point them to this URL. All right, so back to JupyterHub. So most of you in this room are probably more than capable of installing your own Jupyter Notebook server on your own machine, but this quickly starts to break down if you're running a large class for people who don't come from computer science backgrounds, or if you're in an enterprise situation and you perhaps have some people who are not familiar with the Python package management ecosystem. So you very quickly run into a massive headache. You have compilation errors, installation errors. People start having what's known as an installation drift. So someone has version X of some kind of Python package, and another person has version Y. So you get, it works on my machine situation, but not on everyone else's machine. In addition, in classes, for example, if you're teaching a Python class, you might have people who have Windows machines that don't have administrator privileges, for example, and this can be a problem for some packages. So a solution to this is to deploy a unified environment in the cloud using JupyterHub. So let's take a bit of a look at JupyterHub internals and what's happening. So we have two familiar components here. We have the user's browser, which is what all of you use to interact with your single user server. And then we have the Jupyter Notebook, which is the component that actually listens to your command, talks to the Python kernel behind the scenes to execute your code, and then sends the results back to your browser to display to you. JupyterHub sits in between these two components, and it has three main tasks. So first, authentication. This is super important. We're going to be letting people execute code on our servers, so we have to make sure that we only allow it for people who are authorized to do this. Second, check if a user is new. If they don't have a previous Jupyter Notebook server running, then we have to spin up a new server for them and redirect all of their browser requests to this server. If we already know this user, then we simply have to redirect. So what actually happens behind the scenes when you deploy JupyterHub is you get two components. You have the actual hub, which is a Python process that leverages Tornado. It does all of the main logic behind JupyterHub. So it authenticates users, and then it spawns the single user Jupyter Notebook servers on a machine of your choice. Now, there's a second component here that's probably not as well known, and that's the proxy. This is the public-facing component of JupyterHub, and it's the first component that receives a user's request when you try to interact with Jupyter through the browser. So the proxy actually has several jobs. First, it checks if it already has an entry for the user in its dynamic routing table. If it does, that means we've already seen this user and we've authenticated them, and that means we can simply redirect their requests to their server. If not, then the proxy redirects the user's request to the hub, which then sets up the server for the user and adds a new entry in the proxies table so that the next time the user talks to the proxy, they can immediately be routed to their single user notebook. So there's a live system running there. So if you saw the URL where I was doing a demo, behind the scenes, this is what's happening. This is a Kubernetes cluster. I'll talk about Kubernetes a bit later in the presentation. But this is running on Google Cloud, and as you can see, there are several pods, which is just an abstraction over a process. And you can see there is a hub, which does the authentication and spawning, and there's also a proxy, which is the public-facing component. And then there, by the looks of it, there is one notebook, which is the one that I started. So if we run this again, okay, someone else is on the system. That's great. So if we take a look at the proxy logs, we can quickly see that this new user, whoever you are, thank you for trying it out, they've logged in, and the proxy has talked to the hub, authenticated the user, and then it's basically added a new entry into the table so that next time the user uses the system, they'll be automatically routed to their single user notebook. Okay. Yeah, sorry about that. You can upload your own, I think. But okay, let's keep moving. So let's talk a bit about what happens if you want to deploy JupyterHub in production. So what are some of the challenges that you may face? So first of all, you have lots of users on your cluster, so you need to manage CPU and memory resources responsibly. Whether a user is malicious or not, they might accidentally start up some kind of thing that takes up all of the available CPU capacity and memory resources and cause everyone else's performance to suffer a lot. So that's probably number one of your concerns. You have to manage cleaning up resources. If you're running a large class of, let's say, 1,000 users, you won't be able to do all of this manually. You have to be able to scale your compute resources up and down depending on the load. So if you're running a data science class, for example, and everyone logs in at 8 a.m. and you have 1,000 users, you have to be able to handle that without manual intervention. And then last but definitely not least, you have to worry about security, especially if you're in an enterprise environment and you're handling some kind of sensitive data. You have to be able to secure the connection between the browser client, the Jupyter server, and also whatever the Jupyter server talks to in order to get the data. So let's step aside from the data science aspect of this for a moment, and let's talk about some of the recent developments in the infrastructure software engineering space and see how those can help us address these challenges. So first of all, something that you've all probably heard about is containers. So a container is a logical concept that uses a collection of features introduced into the Linux kernel to isolate processes from one another and to make sure that they don't use more CPU or memory than is allocated to them. So basically, it's like lightweight virtualization that uses the host machine's operating system. Although it's been very popular in the past 10 years, container technology is actually by no means new. It's been around since the 1980s in its earliest versions, but it didn't really take off until 2006 when Google contributed a Linux kernel patch that introduced control groups, which are one of the key features that enable modern container technology. Containers didn't get particularly popular until a company called Docker made it very easy for people to create container images that could be shared through repositories to store them and to run them remotely. And yeah, as you can probably tell, the container space has certainly exploded since then. So containers solve the first challenge that we have. They isolate the process, and they also make it very easy to deploy applications that have dependencies, such as Python data science applications. You might have dependency on NumPy, SciPy, lots of other different things. So containers solve those two things for us. So for a JupyterHub installation, we would need a container to run a Jupyter Notebook server for each user. Depending on the number of users on your platform, this could be in the thousands. We also need something to run the hub and the proxy, and to make sure that those are running through the whole duration when our system should be up. So for a small deployment of 5 or 6 people, you might be able to do this manually, packaging them up in containers, then logging into whatever server is going to be serving this, and running the necessary commands there. But for larger scale deployments, you need to think about what if your machine fails? Whether it's an on-premise data center or a public cloud, it's possible that it would fail and you would have to default to another availability zone. What if you have to redeploy something while you have active users? What if you have to load balance users or redirect them to another data center? So those are the kinds of things that it would be very hard for you to do if you had lots of users and you had to do this manually. So in the infrastructure software engineering space, there have been several solutions to this problem of managing large-scale containerized applications that need to have high availability. And these are known as container orchestrators. They take care of two main things for you. So first, they manage a cluster, which is a collection of cloud-based or on-premise machines that, from the application's point of view, look like a single machine. So your JupyterHub single notebook server shouldn't actually care which actual physical or virtual machine they're being deployed to. And what handles this deployment is the orchestrator. It schedules and manages containers. It makes sure that there's adequate compute power on the virtual machine where the container is scheduled. And it can also do things like failover and act as a self-healing system. So if a node in your cluster becomes unhealthy for whatever reason, the orchestrator can deal with this. So if you go back to the JupyterHub project, there are many, many container orchestrators that are in use these days, but the JupyterHub project has chosen to go with Kubernetes, which is an open source orchestration system that was first developed at Google to handle their large-scale or container application loads. So what Kubernetes does in a nutshell is it has a master component. This component manages a cluster of nodes, which are, for example, virtual machines on your favorite cloud provider. And it takes care of scheduling containers, scheduling applications, load balancing, failover, and making sure that the state of the cluster is always in the desired form. So there are two key things that have been very interesting about Kubernetes. So first of all, Kubernetes has introduced what's known as declarative infrastructure definitions. So 10 years or so ago, when you were first preparing your server to deploy your application, you could potentially SSH into the machine and then run a bash script or run a series of commands that would prepare your machine to host your application. So these days, that's known as an imperative infrastructure definition, and it's no longer in use. So instead of, it's no longer in use widely, I should say. I'm sure there are still places that, that provision infrastructure in these ways. But what's different about Kubernetes is that instead of defining the steps that should be taken, you define what you want the state of the infrastructure to be. So for example, I could say, I want 3 replicas of JupyterHub running, but I don't tell Kubernetes how to get to 3 states. Instead, Kubernetes continuously monitors my JupyterHub deployment, and when it detects that, for example, one of the JupyterHub processes has failed, it's going to try to be self-healing and bring up another process to replace it. The second thing that's important is abstracting of infrastructure. So instead of dealing with the actual physical virtual machines and network interfaces, we're dealing with abstract objects such as pods, which represent a process, or services, which represent logical sets of pods and an access policy that users can use to access them. So in theory, at least, this should make it easier for people who aren't very familiar with infrastructure to run applications on Kubernetes. So this is basically how you define a service in Kubernetes, is you write a configuration file and then you deploy it to the server. For small applications, once again, this is okay, but if you have to write a lot of YAML, you will very soon have a bad headache. So what Kubernetes does is it has a package manager called Helm, and there are two components in it. One of these components sits on your client machine, and the other one, Tiller, is on the cluster. So your client machine talks to Tiller and tells it how to deploy applications on your Kubernetes cluster. And this is also the route that the open source JupyterHub project has chosen to go to. So they basically provide a Helm chart for you, which makes it really easy for you to deploy your JupyterHub applications once you have your cluster up and running. So to prepare for this presentation, I tried to deploy JupyterHub on 3 different commercial cloud providers and compare a little bit the costs and ease of deployment in doing this. So as you might know, Google, they sort of have a monopoly on Kubernetes services, at least until recently. So they have an offering called Google Kubernetes Engine, which is a managed solution. This means you don't actually need to know too much about running Kubernetes because Google takes care of that for you. So the good thing about this is that things usually work out of the box. You can check out the JupyterHub Helm chart from GitHub, run a few commands on your local shell, and you'll have a working JupyterHub running quite quickly. The other nice thing about this also is that you only pay for the Google Compute Engine instances that make up your nodes. You don't actually have to pay for the machines that run the Kubernetes master itself. So if you want to try out a small cluster for your JupyterHub deployment with just 3 nodes, and each of them is 1 virtual CPU and a bit of RAM, you can get away with about an €80 bill per month, and this will be good for a small demo, maybe like 5 to 10 notebooks and nothing too CPU intensive. So next one is AWS. So until recently, AWS had no easy way of running a Kubernetes cluster. Instead, you had two options if you were feeling a bit adventurous and wanted to do some do-it-yourself deployment of Kubernetes. So you can use a guide produced by a company called Heptio and a CloudFormation template, which is Amazon's way of writing configuration for infrastructure components, or you could use a command line tool called kops, which makes it quite easy to deploy a Kubernetes cluster that you manage yourself on AWS. Now, the 2 downsides of this is that you will have to sort of be an expert in how to deal with Kubernetes problems in case something goes down and you have to debug it, whereas with Google Cloud, you don't really deal with that stuff. In addition, you will also have to pay for the virtual machine that runs the Kubernetes master, and it's quite a large machine, so that will definitely add to your bill. Last but not least is Azure Container Service, which is quite similar to the Google Cloud offering in the sense that it's also a managed service, so you don't have to actually deal with installing Kubernetes or deploying any of the components. It is a bit new on the market, so there are still a few hiccups, but overall it works quite well. So I also tried to deploy JupyterHub onto Azure, and it works pretty much out of the box. The very nice thing about Helm here is that once you have set up your Kubernetes cluster, your JupyterHub application is pretty much portable across cloud providers. The only thing that's different is the actual process of setting up the cluster. But once you have that installed, you can just use Helm, and all of a sudden you can deploy to pretty much any cloud provider that supports Kubernetes. So I tried to compare the Azure Container Service with the Google Kubernetes engine in terms of cost. And although the 2 providers don't have machines that are exact replicas of each other, I found this one, which was quite close to the one I used for the Google Cloud cluster. And it's also 3 nodes with 1 core and a bit of RAM. And the bill for a month, if you leave it running 24/7, is €98. So they are quite close in terms of cost. So if you work in a company and you want to try out JupyterHub on Google Cloud, I suggest coming up with this kind of decision matrix that will help you make a technical decision. So when I work with teams that need to make a technical decision, we usually write the things that we care about. Is it easy to deploy? How well can I use Helm charts? What is it going to cost me? And so forth. And then we go across the cloud providers and we see how well they check our expectations against it. So for example, at the moment, I probably would not go with AWS until they have a managed Kubernetes service, just because you need another team to take care of your Kubernetes deployment, or at least someone who knows what they're doing. So when I gave this talk at PyData London a few weeks ago, lots of people came up to me to talk about scaling and how easy it would be to run this at a very, very large scale. So the things that you need to think about here first are how many users you will have and what kinds of workloads will they be running. If users are just using this to learn Python, for example, it's very different than doing some large-scale matrix computation or computing fractals. You also need to think about how the spike of load is distributed. So if you're running a class, it's very likely that everyone will want to log in at once. If you are deploying this for a team, it could be true that the load is more distributed across the day. But either way, the open source JupyterHub project has provided a handy Python notebook that you can use to estimate your costs, and it's linked on the slide. There's also a very nice case study from a data science class called Data 8, which had 1,000+ users. And the notebook that's behind the link will tell you a bit about how they've budgeted for their class to make sure that they stay within limits. Now, last but not least on this slide is a very, very interesting talk by Scott Sanderson, who works at Quantopian. I don't know how many of you have heard about Quantopian, but it's a community for doing algorithmic trading in Python, and they run their data science infrastructure on JupyterHub. And so in this talk, he talks about running JupyterHub for 100,000 users. It's quite impressive. In addition to mentioning how they do scaling with multiple JupyterHub instances and load balancing users between different JupyterHubs, Scott also talks about managing state with Postgres. So definitely recommend watching this talk if you're planning to scale up JupyterHub to hundreds of thousands of users. So in summary, we've seen what the Jupyter project is, what the ecosystem is, and how to make it easy for you to provision large-scale JupyterHub deployments with JupyterHub. We've taken a look at some of the things that go on in JupyterHub under the hood, and also the infrastructure components such as containers, Kubernetes, and others that make it very easy for us to deploy JupyterHub in the cloud. So I believe I'm doing okay for time, and there is time for questions. So this is all I had, and I'll be happy to take your questions now or through email.
You're perfect in time, thank you. As a data scientist myself, I found it very useful, so thank you again. And does anybody in the room have a question for her?
Sorry. Yeah, thanks for a nice talk. I'm going to ask something maybe a little bit off topic, but is there any chance of running JupyterHub on Windows these days? As I work in a hospital, and they believe in Windows, so...
Do they believe in Windows 10?
Not yet.
Okay. There is Windows subsystem for Linux, which is what I actually have running. So I think this might, it actually gives you a shell with a distro. So I believe that this could be the answer if you want to run it on Windows. But unfortunately, I know the project maintainers have said no to Windows a few times. So unfortunately, I think the answer is no for now.
Okay, thank you.
Hey, thanks for the talk. It was great. Do you have any advice for running CPU-intensive notebooks? Like if you have a team, like how do you manage the resource allocation and these kind of things?
I think at this point, based on my research, you will have to do a trial run first. So you would start with a very small, cheap cluster and then have a few sample notebooks and start up like 10 servers at once and see the time it takes for that CPU-intensive resource to execute, and keep monitoring your cluster through some of, for example, the built-in monitoring tools. But unfortunately, I don't think there's a systematic way yet to determine how many nodes you would have up front. You just need to experiment.
Hi. Do you have any documentation support for handling authentication, for instance, with LDAP, that the helm charts can be edited to handle your internal LDAP server?
So there is a whole guide about doing authentication with different kinds of providers. You can do authentication if you have just Linux users, for example. You can map them. You can use OAuth with GitHub, Google, a wide variety of things. And there's also an LDAP authenticator, I think. I haven't set it up myself, but I believe I saw it in the doc. So there is a support for a wide range of authenticators.
I have a scenario. So, for example, in a classroom, if many students are trying to use the same data set, it can. So there's a lot of duplication essentially in the RAM. So is there any clever solution to deduplicate in some way to reduce the usage?
Do you mean your students all download the data set from like an S3 bucket or something?
Let's say they all download the MNIST handwritten digits database. It's like 100 times the exact same data set in the memory. So
you could attach some kind of volume and put the data set there, and then everyone could access it.
yeah, but still, it's all in the RAM. So when they
Yeah.
load it into, so there's no solution.
Well, I mean, if your students are manipulating the data set, I think it would be quite dangerous to have them share it at the same time. But I don't know of any solution that would help with that.
Okay, thanks.
Any other questions? All right, so thank you very much, Camilla. Please give her another warm applause.